episode 93, Baby Galaxies. And welcome back for another edition of the Syzygy podcast. My name is Chris Stewart, sitting in the office of Emily Brunsden here at the University of York. Emily, how you doing?
I'm doing very well, thank you.
We are back for another episode in which we are continuing the theme of baby things in the universe. For all the obvious reasons, Emily, I have to check in. How you doing? How's everything going?
Very well, thank you.
Good. Still big major thumbs up there. So, yes, given that Emily is going to be going through her own baby adventure not too far down the track, we figured we'd do a little series of podcasts on baby things. And so today we're going to, I guess it's a continuation of a theme. We started with the baby universe itself, the birth of the universe, the creation of the universe. And then we went on to the very first stars in the last episode. Emily, where are we going today?
Well, we're not actually going too far along in time to begin with, but we're going to start looking at the very first galaxies.
Very first galaxies, baby galaxies. So, how do we start this?
Well, I guess the first question you might want to ask is what came first? The stars or the galaxies?
The stars. And this came up in a previous episode because there was when you were discussing what the very first stars looked like, they were kind of interesting. And there was this little bit of a notion of, like, what does it even mean to have a bunch of stars, a cluster of stars, when you've got these big, strange, wobbly stars that are made out of only the hydrogen and the helium and nothing else, because there was nothing else around. But they're huge and they're weird, and they might even have little stars orbiting around really, really big uber stars. So the whole notion of a collection of stars is kind of a bit hazy at that point anyway. But it is an interesting question. Do you get stars forming in larger structures, which would then become sort of galaxy things? Or do the stars form and then the galaxy structures form after them? I don't know.
It's all about strange, isn't it? Well, I think because we have such a clear definition of what a star is, right? We know that when a sort of collapsing cloud of gas comes down to the point where it gets so hot and so intense in pressure in the inside that you start fusing hydrogen to helium, that's a very clear cut. That's a star. That's, we know, we can look at that. Everyone will point at that thing and say, yes,
that's a star. It's a ball. It's, nuclear burning. It's doing its thing. That's a star. It's clear.
Yep. Whereas a galaxy, I mean, we sort of have in our minds the glorious pictures that we've been treated to over the last few decades of Hubble, of beautiful big spiral galaxies, these structures, these really fascinating objects. But really, I think we need to dial that sort of imagery down a little bit, because although these big grand spirals, etc., do exist clearly in the universe today, there are lots of other different types of galaxies. Some of things which you had a look at, you wouldn't even recognize as a galaxy, and maybe even some things you have looked at in the sky and not recognize that is
not even
a
realize
galaxy.
what you were looking at. So we'd probably then, by the sound of it, need to start with, Emily, what's a galaxy? If we're going to talk about baby ones, then how do astronomers define galaxies?
Yeah, it's a really good question, and I'm not sure if there's really a particular definition.
You know it when you see it.
Yeah, there's very few things in astronomy that do have very clear-cut definitions.
You know what? For a science, you're very vague people.
Well, it's one of these things, again, you know it when you see it, right?
Yeah.
But so just to sort of give you a view of kind of the zoo, if you like, of different types of galaxies we have. We do have the big spirals like the Milky Way, Andromeda, blah,
your
blah, blah.
quintessential, that's your beautiful galaxy that everyone knows and loves.
Yep.
And we're in one, right? The Milky Way is one of these, beautiful spiral-armed galaxies. And so that's what you kind of think of.
Yeah. And then you see these kind of other really large blobby galaxies. They kind of look like either spheres or can even be kind of long cigar shaped. These we call elliptical galaxies, and they're huge. They're at least as large as the spirals, but usually even bigger. So they're really kind of just clumps of stars, but maybe don't have quite the structure that you would normally see in spirals. And then we actually have two other definitions. We have irregular, which is...
Let's just lump all of those together that look weird.
Yeah, basically the other category. Quite often they're things that are merging at the moment, so two galaxies coming together, so they're sort of getting pulled apart. Or a galaxy that may have been part of a merger in the past and is now it's disrupted its structure. It doesn't kind of look normal anymore.
Right. Okay. So it could have been something fairly simple, but it's not anymore. And so put it in this group over here, then we'll call that irregular.
Yeah.
Yeah. Okay.
But the interesting one, I think one we'll come back to today, is looking at our dwarf galaxies.
Mm-hmm.
Now, when we talk about galaxies, like all the ones we've mentioned before, we're talking about sort of structures which have hundreds of billions of stars, right? The Milky Way has maybe 300, 400 billion. Andromeda's got a few hundred billion more than that. But then these really tiny sort of small dwarf galaxies. We're really talking about things that only have maybe sort of a few tens of millions maybe of stars.
Which is like, that's still a big number. But in terms of numbers of stars, when you're against billions or tens or hundreds of billions of stars, tens of millions is tiny. Like that's a fraction of a percent.
But yet these things are very, very common. These are little dwarf galaxies. Right. In fact, we've kind of got our own like groupie collection of them as the Milky Way galaxies. We're the big people,
right.
if you like.
Yeah.
And then we've got our little collection of fans.
Right, hanging around the edges.
These little dwarf galaxies.
So which ones are those?
Well, two of them you're probably familiar with, because being a southerner particularly. And if you have been in the southern hemisphere and even looked at the Milky Way galaxy, you will have surely seen these.
You might not have known what you were looking at, though.
Might
Are those
not have
the
known.
Magellanic
clouds, yeah.
Magellanic, isn't it? Yeah, because it's Magellan.
Yeah.
So Magellanic clouds. Large and small, is that right?
Large and small, yeah. There's kind of two little fuzzy blobs on the sky that sort of appear on one side of the Milky Way. And yeah, if you sort of just look at them, you might think, oh, someone has had a bit of a sneeze. And
sneeze on the night sky.
We just need to sort of wipe that bit up.
Yeah, because it's not like you're looking up and go, oh, look, there's a blob that's filled with stars. It's just sort of a bit of a smudge, really.
But you might not have realised, but that you're actually looking at a different galaxy at that point.
That's very cool.
So those are the two naked eye sort of extra galaxies. You can, if you know what you're doing, know where to look, you can actually spot Andromeda if it's very, very dark as well. It's the reason actually why Andromeda is so hard to spot is not that it's bright. It is very bright. It's actually that it's huge on the sky. So that brightness is spread out over a big area. Yeah. So it's actually quite hard to see.
So if you take a picture of a really long time, then, long exposure, then it shows up really nicely. But just looking at the sky, it's not leaping out at you.
Yeah, that's right.
Yeah. But the Magellanic clouds, those galaxies, they're dwarf galaxies?
They're dwarf galaxies,
yeah. So how big are they?
So the Large Magellanic Cloud has about 10 billion stars in it.
10 billion, okay.
Yeah. And the small, about 6.5 billion.
Right,
so.
Okay. But you said before that dwarf can get down even much smaller than that. You can have groups of stars which aren't in the billions, which are in the millions. Yes.
Well, this is where we get to some interesting stuff. And we're going to loop around back to what these kind of galaxies might sort of have been in the past. But yeah, typically our dwarfs that we see around us today, we're talking about low number of billions.
Okay, all right. So is there a cutoff? Is there a sort of that's a dwarf, that's not a dwarf, and it's at this number of stars? Or is it, again, you know it when you see it? Is it contextual?
It is contextual. So, right. You've got a clumping of stars that's not part of, it's not part of a dynamically, gravitationally, actually in another galaxy. So we have clusters of stars, for example, in our galaxy, but they are part of our galaxy. They're all encompassed in the Milky Way. So you've sort of got to be a bit separate. Right. And then, but
not too big.
No.
Not too big, and then you get to be a dwarf galaxy. Okay, cool. All right. So that's dwarf galaxies. Fantastic. But how does this relate to first galaxies?
Well, let's come back to the very, very beginning where not so much the beginning. We went from the Big Bang all the way up to the first stars and the first one in this little mini-series. We then talked about the first stars themselves and when we sort of think that they started. And the most recent research is telling us maybe 250 million years after the Big Bang was when our first stars were being born. Mm-hmm. So now, when were the first galaxies formed? And did the galaxies form and then the stars formed? Or did the stars form and then the galaxies formed?
Yeah, chicken and egg question. So?
Well, we don't really know.
Good. Right, end of podcast. Thank you for listening.
Yeah. We know that at least 400 million years after the Big Bang, galaxies existed.
Okay, so this is sort of putting you can put a lower limit on this. Is, well, what's the earliest galaxies we see? And even if we can't answer the question, which was first, like what happened before then. At least we've got a lower bound.
Yeah,
right?
yeah. We're not even quite seeing these ones. So the earliest ones we can see are kind of 500 million years. That's going to all change in a matter of a few months, which we'll get to. But at the moment, this is kind of our limit of what we can see. So we know that, just backtracing from that, if that structure exists at 500 million years, then it had to exist at 400 kind of thing. So maybe it was earlier as well. But so sometime in those very early few hundred million years of the universe, then the galaxies formed.
Right.
Now, yes, so coming back again, you might feel like I'm avoiding this question.
You are being a little bit
What
evasive.
came first, the stars or the galaxies? It comes back down a little bit to your definition of what a galaxy is. So do you count a clump of gas that was just kind of a little bit denser than the next bit of the universe? Is that a galaxy?
Is that, what counts? What defines it?
Or do you need to have a star in your galaxy for it to be a galaxy?
And will one star do? Like if you've got a clump of gas which is a little bit more dense than the other gas around it, it's got one star in it. Is that a galaxy? I don't know. You tell me. This is your
It's
job.
a difficult question. And I'm not even sure that astronomers particularly care about the answer to this question. But I did try and read as much as I could to figure out, this chicken and egg sort of scenario.
But I mean, it's like at some point you've got to grapple with this, right? If your interest, I'm not saying you specifically, Emily, I'm saying if one's particular interest is about like when did and how did the first galaxies form, then at some point you've got to kind of grapple with what do we mean by that? What does the question even mean? And I guess one way of getting at it is what's the earliest galaxies that we can see that look like galaxies, and then work backwards from there to say what did it look like before that, and not worry too much about was it a galaxy at that point, I guess.
Yeah, and you're certainly bang on the money when it comes to the question of how did these galaxies form. That is definitely a topic of much interest to astronomers in trying to figure out how these first galaxies came about. Unfortunately, the very short answer to that is still, we don't really know.
I see a pattern here.
But we have a lot more information, and we have two very clear models about galaxy formation in the very, very early universe.
Okay, well, two is good.
Yeah.
Two is good. It's much better than none, and probably more comforting than one. If there was only one, but you weren't sure if it was true or not, then that doesn't really lead you anywhere. Having competing models is at least something you can play with.
Well, I mean, they are really the only two ways you could possibly form a galaxy.
Okay.
So if you had a third, I'd be a bit confused. But
All right,
anyway.
that's nice and complete.
So there's two ways you can form a galaxy. You can have a very, very large clump of stuff in the universe that collapses down and forms something smaller. That's called a top-down model of formation.
Yeah.
Or you can have little things that come together and get bigger and bigger and bigger, and that is bottom up.
That's a bottom up, right. Which, again, I remember talking about this when we were talking about solar systems and creation of solar systems and so on, and that you can have top-down and bottom-up of the way planets are formed and things like that. So a similar idea here.
Yeah.
And so those are the two...
I can't imagine
models?
a third that you could get out of the universe, to be honest.
It's going to be one of those or the other, or maybe a combination of both. Who knows? But yeah.
So if you have a look at the different models, so top down is it's a very natural place you might go to as an astronomer, because you see structure being formed in this way in other parts of astronomy. For example, the birth of stars is a top down process. It's a collapse process.
Right. You've got a bunch of gas and then a little bit, which is a bit denser, collapses further and further and further. And out of that gas, you get this really dense bit that eventually switches on as a star. But that's a top-down thing.
Yeah.
You started with big space filled with stuff and creating things out of that.
So this model's been around for a while. It was first sort of really put together in its form that we know today in the 1960s. But it just follow basically the same principle. Gravity pulls matter together. Dark matter, we know now, probably played an important role in that, helping that structure to form. It clumped, it collapsed down, and then it got to little clumpy bits that went under their own self-collapse. And then you sort of get this really natural thing forming out of top-down models, which is that... So we talked about how we form disks when we form planets, and actually the same sort of thing happens in the top-down model when you form a galaxy, because what you're doing is you're getting smaller and smaller and smaller, but the object that you're getting smaller and smaller and smaller has some rotation.
Just randomly at the beginning.
Yeah.
And that rotation, if I remember correctly, that the effect of a very small amount of random rotation is going to be going in one direction randomly more than any other direction. And that gets enhanced as it collapses, right?
Yeah.
That all the other random motion basically cancels out and you're just left with what on a massive scale was a tiny little bit of it's just rotating this way a bit becomes this whole thing is swirling around in that direction as it collapses down.
Yeah.
And that's how you get a disc.
Yeah,
in a plane.
It's what we call the pizza dough model.
Right, nice.
Which you can imagine if you're a very, very good pizza base maker.
Then, a pizza twirler.
Yeah, then you can spin your initially spherical lump of dough and it flattens out into a disc. It's actually the same piece of physics.
Which I don't know if you've ever tried. I've never managed. It's really hard.
I've only ever made a really, really big mess.
Anyway, that aside, I like the idea.
Yeah.
The pizza dough model.
And of course, angular momentum conservation means that as you get smaller, because you've got some rotation, then the smaller you get, the faster you end up rotating.
Right. It's the pizza dough mixed with ice skater model.
Yeah.
Ice skaters with pizza dough. Pizza dough.
That would
twirling
work
ice
quite well, I
skaters.
think.
Yeah, it's cold though.
But I think,
Anyway,
anyway,
yes, let's not dwell on that too much.
So then you get this kind of spiral structure, which is the kind of the foundation of a spiral galaxy that we see around in the universe today.
Right.
And then parts of that would have been overdense and collapsed down and formed stars, etc., etc. Now, you can explain some of the observations of what we see in the universe around us today with this model, but actually we're more leaning towards actually the flip side of this model because it's all just about what the observations match up better with, to be honest.
I mean, that's the thing about models is it sounds great, really nice idea, but does it fit with the universe? Nature doesn't give a damn about what your favorite model is. It's only going to say this is what we have. So
we haven't thrown out this model yet, but we're sort of leaning towards, in fact, in my notebook, I had to draw a little set of scales with one sort of leaning a little bit more towards actually the other model. That
Emily has the most amazing set of notebooks. We really should, in some way capture these for posterity because I think this podcast it would make a good textbook, I think, in some ways. Very odd. Anyway.
Yeah, so our little scales are bent a little bit more towards the bottom-up formation scenario.
Okay.
So this is actually, we do see this in other places in the universe as well. It's not unfamiliar to us in astronomy. So we get smaller things sticking together to form bigger things. So where we've probably mentioned this before is in the formation of, say, rocky planets.
Yeah.
Dust sort of grains, get to sand, cars, etc. You just stick more stuff together and then you eventually get to the size of a planet.
Yeah, I mean, this is where we've come from. This is the Earth. Right? The Earth formed in that way.
Yeah. And I guess in some ways you could maybe even say a baby's formed that way because you've got sort of cells that are dividing.
Yeah.
Taking up some mass and sticking together.
The baby's not sort of condensing out of the insides of you. It's growing a bit at a time and you're adding to it in small lumps. So yes, I think that probably works.
Yeah, it would be quite disturbing if we had a top-down model.
Very odd
anyway,
mental image.
We'll move on from that.
Leave that one well and truly alone.
So yes, you have small clumps that stick together. Now, what were the small clumps? You might want to ask.
Well, what were the small clumps? I do ask.
It looks like these small clumps were basically what we now call globular clusters.
Okay, so we haven't yet talked, I mean, we've mentioned them before, but in our discussions so far in this episode, we've talked about galaxies and spiral galaxies and so on, and elliptical galaxies and dwarf galaxies. We haven't talked about globular clusters, which are not at the galaxy level, but what?
No, so the clusters of stars. So the globular clusters that we see in the Milky Way galaxy are groupings of stars. They're sort of anything from about 10,000 stars up to a couple of million stars, maybe even tens of millions if you go to really big ones in other galaxies.
Okay, so these are sizable groups of stars, but why do we have them? Why do you get a globular cluster?
Well, that's really interesting because they're really, really densely packed. So they're sort of crammed into this region of somewhere between 20 and 100 parsecs, which sounds like a lot because parsecs just sounds like a really big thing. But if you think about, one parsec is basically the distance from us to the next star.
Okay, so us to the next star That's sort of a star spacing on our scale.
Yeah.
And you said you've got how many in what area?
That's about 1 parsec, and then we've got about maybe 1 million stars and 100 of those.
Okay, so that's a lot.
Yeah.
That's a lot. That's really packed together. You'd know if you were in one of those, because the sky would be very different.
Indeed. You might even not know you're in the galaxy.
That's right, because you're just surrounded by huge numbers of stars.
Yeah.
Wow. I mean, that must look amazing.
Yeah, so and they're wonderful objects to go and look through telescopes and things out there. They're just really cute. Lovely dense, they're sort of a denser central region, and they slowly get sort of more
And we see
rarefied.
these like throughout our galaxy? Like they're
Yeah,
common?
they are. Well, we think we know of about 150.
Right.
There's probably maybe around 500 in total in our galaxy. We just haven't found them all. They're on the other side of the galaxy. Hard to see.
Hard to see. Yeah.
But yeah, so they're reasonably common in our galaxy. They're in a weird place in the sense that all the clusters of stars that are new clusters that are born now, or forming new stars right now, they are all in the spiral arms of the Milky Way, kind of where there's lots of gas and so on to actively form new stars.
Mm-hmm.
These globs tend to sit out in the halo of the galaxy where there's no gas to form new stars.
Right. So they're old? Like, what's the origin of
They
them?
are really old, actually, and this is what makes them also incredibly interesting to study. So it was, for a long time, I think even when I was an undergraduate, we had age estimates for these globular clusters, and there were a couple of them that we thought were older than the universe.
That's embarrassing.
Yeah.
Inconvenient.
It was
presumably wrong.
well, it tells you just how old these things are, right?
Yeah.
They
to
are
within error bars of both the age of the universe and the age of the globular cluster, it seems like they're older. How do you measure that, by the way?
So you can measure it from the ages of the stars themselves. So you know that if you're a particular mass, you know roughly how long a star of that particular mass has to run when it's just fusing hydrogen to helium.
Right.
And so you can kind of measure, therefore, what the age is of the whole cluster based on those, just the ages of the stars in it, because they're all born at the same time. So you kind of get a nice spread.
One assumes that the ages of these things has been updated and it's no longer a problem.
Well, actually, it was almost more the other way. We fixed the age of the universe.
Ah, well, that's that's better. Yeah, as long as we don't have a paradox here anymore, it's fine.
No, we used to think the
happy.
universe was maybe around 13.45 billion years, and now we're much more in the 7-8 billion years.
But I mean, that is pitching the age of these globular clusters to be like, this is not old, this is really old.
Yeah,
like
yeah.
Earliest bits.
So I saw one of the latest studies that's about the average age of the clusters in the Milky Way might be around 13.35 billion years.
So that puts them at the, sort of 400
4 to 500
year
million
mark
years,
after the Big Bang, that's really early.
Yeah, which is right when we're talking about, right?
Yeah, okay.
So it's exciting. We've got these kind of things in our galaxy today, which are potentially some of the very first structures that were formed in the universe.
That's really wild.
So we think that these globular cluster sort of size objects then sort of started to come together into larger and larger structures. And for some reason, some of them kind of just didn't make it into the sort of the full galaxy. They didn't make it into the disk. They just got left out, hanging out in the halos.
Just hanging around the edge.
Yeah.
Nice.
But this whole model really does predict a lot of the things that we do see. It's not perfect. It predicts, for example, that we've got lots of more smaller galaxies in the universe, these dwarfs, which we see, which is good. Tick.
Is that because if you're building things up from smaller things, then you will tend to have sort of a hierarchy of lots of little things making smaller numbers of bigger things, making smaller numbers of bigger things, making smaller numbers of really big things. And at some point you sort of reach, we've got, you'd expect there to be quite a few of sort of smaller size galaxies and really huge galaxies, not so much. Is that kind of where it comes from?
No, you're on the right track too. And you get a whole lot that get left out of the process.
Yeah.
It's different sort of stages. Yeah. So they kind of just become the remnants of the other galaxies.
That kind of makes sense.
Yeah. So that kind of works. There's a few things that this model doesn't really address. I won't go into too much of the details, but basically spiral galaxies are still, they spin too fast as part of the problem. We don't really understand that. And how big spirals are, we sort of think that they maybe should be a little bit bigger, perhaps, than they are. But
I mean, look, to a lay, naive person, I find it amazing that you can take a model like, let's build up galaxy structures, bottom up from chunks to bigger chunks to bigger chunks, and that you can actually make predictions at the level of how fast would you reckon a spiral galaxy ought to be turning on the basis of this model. I mean, that's several layers deep on the the sort of predictive outputs of this model. That's fairly impressive.
Yeah.
To then be able to say, it doesn't quite work.
Yeah, I mean, I maybe trivialized it a little bit. It is a serious problem, and it's a serious problem not only just for galaxy evolution, but it's a serious problem for our cosmology, because our very simple model of the universe, which seems to hold up to most of the tests that we can throw at it, which is called lambda CDM. So that means we've got dark matter, we've got dark energy, and basically it's a very straightforward sort of way to write some equations down about the universe. This is
the summary of our best knowledge of how the universe works. Yeah.
And as I say, it's a great theory. Everything we seem to throw at it, it seems to do fairly well. It's the best thing we've got. But it does not quite explain everything.
It's a bit fuzzy around the edges.
Might need some tweaking.
Yeah, like the standard model in particle physics. Does a really good job as long as you don't look too closely over there. That bit, because it completely falls apart over there.
But don't look too closely at the spiral galaxies that we see around us today.
I mean, they're beautiful, but just don't ask too many deep questions. Yeah.
But so broadly, I think we're sort of leaning this way in terms of structure formation. But, there's actually, as you actually had said yourself earlier in the podcast, it doesn't have to be one or the other.
No, this is not a binary, surely.
You could have had a bit of both going on. So you might have had some collapse on the scales of globular clusters, and maybe these, what we now call globular clusters, what they would have been in the early universe, they might have been slightly bigger than what we see more often today. So that's why sort of pushing up to the tens of millions maybe of stars. Maybe those structures kind of formed from collapse, but then they came together in a more sort of hierarchical merging system. Right. So, there's kind of different ways you can bake the pie to get the galaxies out today.
Inevitably it's going to be more complicated, right? That just because we're clever enough to come up with a model which works reasonably well doesn't mean that the universe is going to behave itself and say, oh, yeah, no, you're right. It was that, definitely. It feels to me like it's much more likely that it would be, dominated by certain processes, but other, top-down type things would be mixing in there at some level anyway. So,
yeah, there's always the outliers as well, right?
Yeah, stuff around the edges.
So we can't quite see back far enough into the universe or far away enough in the universe to quite see these early galaxies, these early stars. We're literally right on the cusp at the moment with our current technology. We discussed
this last time, I seem to remember, that you can get close, you can get so close, but there's still this gap between not being any stars and galaxies and what's the earliest ones that we can see. And I guess the interest there is how far can we push that?
Yes.
How far can we look?
So, we're going to be able to look deeper soon. We'll come back to that. But in the meantime, we're kind of stuck with what we've got. And therefore, it makes sense to now turn our focus a little bit from maybe the first galaxies forming in the universe. And let's have a little look at maybe some galaxies that might be forming in the universe today.
Does that... it's an interesting thing in its own right anyway, because, a dynamic process of formation of anything, stars, galaxies, planets, solar systems, is interesting. But looking at stuff that's happening now presumably can give at least some insight as to what would have happened in the early universe, even if the early universe was different to what we see now.
Yeah, well, this is something I completely had not appreciated at all. I mean, galaxies is not really my field, but I just had my blinkers onto this. I just thought, galaxies formed in the early universe. They've done a lot of evolution. They've done a lot of things in their lives between then and now. But, basically galaxies were formed.
That's
and
done
then
now.
We have what we have today.
So the idea of new galaxies being formed now is a bit interesting.
Yeah, well, I completely just, as I say, passed me by. I'm just completely oblivious to the thought that you could be forming new galaxies in the universe around us today. Now,
can I just point out, the notion of today is difficult because we are looking back in time as we look out into space. And so when you say new galaxies forming today, I mean, you're about to get onto this part of the story. Maybe I should just shut up and let you tell it. But how far away, how long ago does today stretch,
Well, not very long, actually, because the system we're going to be looking at today is actually quite a close by system. So I haven't written down the distance to it, actually, but it's one of the closest big sort of spiral galaxy systems to the Milky Way, which means we're probably only looking about sort of a few million years in terms of light travel time, maybe 10.
Right. So we're
not on that order.
Yeah. So we're not talking billions of years ago, billions and billions of years ago. We're talking within millions, which, again, on the age of the universe is nothing. So there's basically now.
Yeah,
cool.
Exactly. So it's a modern universe, shall we say? What's around at the moment?
So why don't I shut up and you tell me the story? What's happening? New galaxies being created now?
Yeah. Well, we sort of knew about this. I even knew about this because galaxies merge all the time.
Sure.
Right. We've mentioned this many times. Milky Way is going to collide with Andromeda.
And make Milkdromeda, which is still the worst name in the world.
It's cool. I like it. But we see you see lots of beautiful pictures of two galaxies coming together: the Whirlpool galaxy, the mice, the antenna. There's heaps of them. So we know that. So I guess if we exclude that, when I'm not talking about that kind of build a new galaxy, that's just
build a new one out of old ones.
Let's just stick two galaxies together and carry on, right?
So what do you mean then? How do you make a new galaxy in the modern universe?
Well, actually, through the same process. So this is a paper that I came across, which was actually published in December last year. So quite a new piece of research from Pasha et al. And what they were doing was looking at a galaxy merging system, which is M81 and M82. So two very bright galaxies that we can see. M81 is another big grand spiral, and you've probably seen a picture of it before.
Yeah, even I, who knows very little about astronomy, I know the name M81. I've seen that one. Yeah.
And M82 is kind of the other one that's the big one that it's merging or sort of colliding with, interacting with. M82 is very famous as being sort of the prototype or quintessential starburst galaxy.
Right. Being what? What's a starburst galaxy?
A galaxy that's just forming a heck of a lot of stars.
Right. Hence the name.
Yeah.
Okay. Bursting with new stars.
Yeah.
Right.
Yeah.
Could have guessed that.
It doesn't look. It looks a bit odd actually. M82 when you sort of see it because it's got this kind of. It's an edge-on spiral, so we don't see their beautiful spiral arms and so on. You just sort of see this edgy-on-y bit and this kind of dusty, flary bit. But if we were able to sort of turn around and see it, it would look kind of similar to M81.
Right. But it's full of loads of new stars.
And the reason why it's all starburst is because, what was it, about a few 100 million years ago, maybe 200-300 million years ago, M81 and M82 had a sort of a flyby.
Right.
They passed really close.
Right. Which is going to mess up a galaxy.
Yeah.
Because there's a lot of gravity going on there.
There's a lot of gravity, there's a lot of mass, there's a lot of momentum, and kinetic energy being exchanged. And that tends to excite galaxies, produce shocks that go through it. And those shocks trigger new stars to be formed.
So that's what's happening in M82.
Yep. So there's two galaxies, and I say this is a merging process. It's going to take kind of another billion years or so for them to kind of do another few flybys and eventually slow down and kind of
because they sort
together.
of get within each other's gravitational influence, and they sort of flash past each other and swirl around, and it's not like they sort of bash together and stick. Right? There's a lot of space in space, but they sort of fling past each other, and there's this dance that they go on for presumably a really long time.
Yeah. So it's going to take about a billion years to sort of dance to finish. But anyway, so we've got these two galaxies, and actually in M82, which we have actually spotted a very, very tiny clump of stuff, which appears to be distinct from M82 itself in the sense that it's not part of the same rotation. It's not rotating as part of the disk of M82. It's a clump of stuff that we can show is actively forming stars. And it seems to be, therefore, this gravitationally isolated clump of stuff forming stars. And it, therefore, is maybe a baby new galaxy being formed.
Cool. So it's in the sense, I mean, you were talking before about the Magellanic Clouds of the Milky Way. This is kind of similar there for M81, that it's this new thing which is not part of the galaxy itself, but is within its sort of, gravitational orbit, if you like. It's there with it. It's hanging around with it, but it's not part of that structure. It's new. It's a new thing in and of itself.
Yeah, and it seems to have been formed from stuff that's been ripped out of
Right.
M82 as this M81's gone past.
So all the bits are there. So now you get to watch it sort of forming into a bigger galaxy.
Yeah, well, we say bigger.
Bigger, yeah.
Well, so let's compare it back down to our large
Okay.
and small Magellanic Clouds. So remember we said the large and small Magellanic Clouds were, what we're talking about, 10 billion stars for the large, maybe 6.5 billion stars for the small. This one we're talking maybe 50 billion stars. So kind of same sort of scale, maybe 5 times bigger.
Yeah, so that sounds plausible, yeah.
But the density of these stars is huge because the large Magellanic Cloud's about 4 and a bit thousand parsecs across.
Mm-hmm.
This one's only about 600.
Right. So that's much more clumped together already. Like they're really dense. And is that because it's basically come from, the existing galaxy and it's been kind of torn apart a bit during this flyby collision with M82? And so you've got a bit of it which has been ripped. I mean, are you basically saying we've just ripped off a bit of a galaxy and now it's
a new galaxy?
A new galaxy?
Yeah, and I should be very clear here that I've been a bit naughty in my terminology about how many stars and so on these things have, because what I'm really talking about, particularly with this new galaxy, is actually the number of solar masses.
Ah, okay.
It's not necessarily the number of distinct stars, because you can have stars that are 100 solar masses, you can have stars that are 0.3 of a solar mass.
But I do remember you saying that the sun is fairly average.
It's fairly
as a
average.
star.
It's still above average mass,
Right,
generally, at least for our galaxy. But anyway, there's 50 billion solar masses worth of material. Much of that may not even be in stars,
Right.
at all yet.
Okay.
So yeah,
Okay.
let's just be a little bit clear. Whereas there's large and small Magellanic Clouds don't actually have a huge amount of gas and dust. They've got a bit, but not huge amounts.
Okay. But that aside, it's not like we're talking about a tiny weeny little bunch of stars, which it's not even a galaxy, and it's not like we're talking. That's like spiral galaxy size. This is something which is in that in between size. It's definitely galaxy sized. So in what sense, in what sense are we saying that this is now sort of forming into its own thing?
Yeah, well, we're calling this a tidal dwarf galaxy.
Tidal dwarf galaxy.
Yeah.
Okay.
So dwarf galaxies, as we've mentioned before, these littler versions of galaxies.
Sure.
It's called a tidal dwarf because it's tidal forces that have kind of ripped it out of its original kind of host galaxy.
Okay. And tidal forces being the kind of forces that you talk about when one galaxy flings past another galaxy and you get a pull on one from the other and vice versa.
Exactly.
Right.
Yeah.
Okay.
Yeah. So now this little tidal dwarf galaxy is there's kind of a few different candidates and there's a few sort of known around about the place. So it's not the very first one to be discovered, but it's pretty clear cut that it's different from its host galaxy. This is kind of one of the better measurements as far as I understand, saying that this is not just more stuff from that galaxy that's just floating out there in space. This is actually now an active star forming region.
Right.
We've got new stars being formed. It really is distinct and it is really kind of its own galaxy in its own right.
Right. Because, it'd be interesting enough if you had a collision process between two galaxies which did deform and mess around with one of the galaxies and maybe a bit of it sort of gets stretched out. But that's not as interesting as, and this bit's just come off. And not only that, but it's now doing its own thing. It's building its own structure and it's making new stuff.
Yeah.
And so presumably that's where the excitement is that while it came from the old galaxy, it's now its own thing.
Yeah.
Which is cool.
It's very cool. And it was the way that they characterized this galaxy to be something very different is actually using... I'm going to go into this because it's just too cool. I know it's not exactly about baby galaxies,
nerd out.
But I've got to tell you about this. It's a new telescope called the Dragonfly telescope.
You sent me pictures of this, and I began by thinking, I wonder why it's called the Dragonfly. And now if you look at the show art, the chapter art for this particular part of the podcast, you'll see why it's called the Dragonfly, because it's really cool. It looks like a dragonfly's eye.
Yeah.
Which is awesome.
So dragonflies are sort of a class of telescope which have been around for a little while, where there was an idea of saying, well, actually building telescopes is quite expensive. Building, specific optics, mirrors, lenses, etc. for telescopes is, it's not cheap.
No, particularly with the trend of, could we make one bigger?
Yeah.
as big as we possibly can. That's going to cost you a lot.
Exactly. And sometimes you don't always want really, really big telescopes. Sometimes you actually want smaller telescopes that are more nimble, that can see more of the sky, that you can train robotically and that kind of thing. And so, well, there's actually other fields in the world who also deal with high precision optics, for example. And of course, the photography industry is a big one of those, right? Photography and astrophotography have always gone hand in hand, and the different technologies being developed. But it took someone, I think, quite clever to sit down one day and say, hang on, you've got basically these enormous, giant, what you might call paparazzi lenses that people use for photography. Aren't they just kind of mini telescopes?
Couldn't we just buy a whole bunch of those and point them in the right direction?
Yeah. And that's exactly what they did. So there's been a few...
Kind of seems obvious when you put it that way.
Yeah, like you just stick a whole lot of telephoto lenses together and you've got effectively a large telescope.
Surely.
And it's much cheaper because these things are commercially available. They're just sitting on someone's shelf, that you can go and buy.
Is that the telescope equivalent of sort of, in the late 90s, early 2000s, everyone in computing went from, let's build a really big computer to, we've got all these computers over on the shelf that we could just go and buy. Can we just connect a whole bunch of those together? And suddenly you've got these massively parallel computers built out of things that you just buy. You don't have to have, Cray build you a massive supercomputer. You just make one. This is kind of the same.
It is, yeah. So it's quite clever. And probably the most famous other telescope that's been around using this kind of technology is WASP. So you might have heard of WASP.
Dragonfly and WASP.
Yeah. Well, and of course you're getting these names from the fact that you put a whole lot of these telephoto lenses together. They kind of look like the eye of a
Yeah, I mean,
insect.
they look so cool.
Yeah.
Yeah.
So WASP has been around for quite a while. WASP was another robotic telescope, and actually there were a couple of WASPs. And Super
Wasp is something we really don't want to encourage.
But the reason why they're famous and the reason why you might see them around is that actually they were some of the very first very efficient planet hunters.
Oh, right, okay.
Because they could study a big bit of sky at any one time and look at very, very small changes in the light from stars.
Right.
So loads of exoplanets were actually discovered through these. So you have ones like WASP 38 or WASP 106 or whatever. And those names exist for these exoplanets to this day. So if you see an exoplanet called WASP,
I shall keep my eye out for the WASPs.
Yeah. But anyway, so this is Dragonfly, which is kind of, I guess, building on that same idea. It's a very slightly different telescope. They're actually doing it for slightly different reasons. They're not really, as far as I can see, interested that much in exoplanets. What they're interested in doing with Dragonfly is taking a really large chunk of sky, which is hard to do with a very big telescope. Normally, the bigger your mirror on your telescope, the tinier the little patch of sky that you're focusing on.
We've probably talked about that, but that's still not an intuitive thing to me. But I guess that makes sense.
Yeah, well, it's just to do with your focal ratios.
Yeah. You want it as big as possible to get as much resolution as possible in as small a space as possible.
Yeah.
Yeah.
So whereas with these sort of arrays of lenses, what you can do is actually see huge chunks of sky at the same time, which is what makes them great for surveys, because you can just sort of get around the night sky in just a couple of hours. Or indeed what with Dragonfly they're trying to do is look at large structures that are very faint but cover big areas of sky.
Right, like galaxies.
Yeah. And so that's why coming to these nearby galaxies is really, really useful. So it's quite cool, what they call low surface brightness stuff. And because you can take this sort of fairly cheap, readily available telescope and point it at the sky for 100 hours, and that's fine. Nobody worries about that because that's, all these tend to be built by institutions to do specific projects. But, if you went and said, Hubble, can you just go and point at this for 100 hours for me? I think they'd laugh.
They'd just laugh you out of the room. Not going to happen.
Exactly.
Yeah.
So that's why I thought this was quite cool. And actually, so this came out of a pilot study of taking this Dragonfly telescope. They only took 3 of the lenses and wanted to do some very basic spectroscopic work with it, or some very basic looking at different parts of the spectrum, just looking at hydrogen lines, just looking at nitrogen lines, and sort of just seeing, what can we extract? Does it compare to all the other studies of these reasonably bright, well-known galaxy mergers?
That's very nice. I saw that
Yeah.
you sent through the picture of both of Dragonfly as it will be. This is the one they've been using as a prototype. So they're building the actual Dragonfly. But the prototype one, the Pathfinder as they called it, kind of looked to me like a three-eyed Wall-E, from the Pixar movie. It's very cute. But it's such a fabulous piece of technology.
Yeah, so it's very cool. So they combined that and they sort of said, well, we've got some signs from these early Dragonfly observations that there might be some star forming going on, and here they did some follow-up work and also confirmed it with other big telescopes, etc. as well. And basically they're saying yes, there definitely are stars being formed.
This is happening. We are
and this
watching
is where they are
in our local bit of the universe right now, new galaxy formation with new stuff happening inside.
Yeah,
that's cool.
So I was really blown away. I was thinking, oh, actually, we are fine. Like, galaxies are being made right now in our sort of part of the universe. Now, how long this galaxy will last is perhaps a question that might be worth touching on.
Well, I mean, do you mean even beyond the fact that it's in the middle of a system which is currently formed from much larger things in the process of colliding?
Yeah,
like
it sounds pretty
knocked
terminal,
apart,
actually. Yeah.
Or do you mean even independent of that, would this thing stick around anyway?
Well, it would be all right if it wasn't in the middle of a merging system.
Yeah, if it wasn't being born in a storm.
Yeah, the problem is that it is born really in the middle of this system that's merging. So as I say, about 1 billion years. There's actually 3 galaxies that are on the merge here. So we got the M81, M82, and another one, NGC 3077.
There's another one? As if 2 wasn't enough?
Yeah, that's going to probably fall in there as well.
Yeah.
So the likelihood of it coming out of all that unscathed, I mean, I haven't run the simulations, but I wouldn't be super confident.
Yeah, you'd have sort of a bit of money on. Yeah, it's probably not going to. I mean, isn't it weird that makes me feel a little bit sad? Like, anthropomorphizing things is silly anyway. But the fact that you've just told me that there's this new little galaxy being formed and it's doing its thing and it's just trying to do what galaxies do, and then it's probably just going to be bashed apart when these bigger bully galaxies have a fight. It just seems wrong. It's not fair.
It does seem a little bit.
Which is ridiculous the moment I think about it, but there we are.
But then if you draw this all the way back to the early universe, imagine that galaxy was formed in the early universe. There wouldn't have been these big spiral galaxies.
No, that's true.
Kicking around. So maybe we'd just found some more friends that were kind of the same size of it, and then it would have built up into a bigger galaxy itself.
Yeah, I'm convinced. So, Emily, you earlier on in this podcast, you'd been sort of talking about how we can only see so far back towards the beginning of galaxies, the beginning of the universe, the beginning of time. We sort of reach this point where we just can't see any further. We can't go any further back in time. But you hinted, and I'm pretty sure I know where this is going. You hinted that that's all about to change, but we'll come back to that, you said. So now's the time to come back to that. What's happening? What's about to happen?
Well, yeah, everything that we've just said in the course of this podcast could become completely irrelevant within the next few months.
Excellent. Good. Because I'm guessing our old friend James Webb Space Telescope is up there getting ready to do its thing, still in the testing phase, but all going well. It'll switch on and do what?
Well, it's going to look slightly deeper than what we can see at the moment. So really, actually, one of the main science goals of JWST is to see, can we see the first stars, the very first galaxies? Can we push that last extra, just a last extra couple of million years back, and a couple of 100 million years back in time to see those? Has
it been, I mean, I'm assuming the answer to this is yes, but also complicated. I'm assuming it's been designed, like its entire parameter set. This is a big, complicated, extraordinary instrument. And part of that has been around, okay, how big a telescope would we need to put into space in order to see X much further back towards the Big Bang? And JWST has got to be surely a compromise around, we can't afford to make it any bigger than it currently is, but this will get us just far enough. Like, are we confident that we're going to be able to see the things we want to see with this telescope?
Absolutely. This has been many, many people's life work, right, to put this telescope together to answer this question, amongst others.
But I guess the flavour of my question is, like, if you, again, I know I often make this parallel, but that's where I'm coming from. Particle physics, right? We can talk about particle physics again for a second. You've got the Large Hadron Collider over at CERN, right? And it was the biggest particle accelerator in the world. And then they made it even bigger over the last decade or so, just bumping up its power in the hope of seeing new stuff and doing calculations and saying, we're fairly sure that we might see new stuff. And as it turns out, it hasn't given as much new stuff because we don't know. We don't know what we're going to see in particle physics when we crank the energy up even more, which is a bit different to the universe because you're pushing back towards the Big Bang. Like those first stars have to be there. Those first galaxies have to be there. So was JWST designed to be able to see them or just getting closer?
Well, the answer is not that simple, unfortunately.
Of course it's not.
I think because when you think about when JWST started its design process, which would have been 30 years ago, let's say, we had no idea about even the galaxies that we talked about in the last episode, right? We had no idea that we could even see those galaxies with the technology that we have now.
Isn't that amazing that it's been 30 years of designing this thing and so much has happened in the last century, let alone 30 years.
I mean, it was only last year that the paper came out saying that these things might be around 250 million years.
Yeah, fair point.
So I think you can make good guesses. I think in any case, they knew they were going to be going further, and that's fine. You can always go further. And there is a point. You can't go back forever. But I think we have hit that sweet spot of probably we will be able to see these things. And it's not, as I say, by accident. It's not just like, hey, we happen to have this infrared telescopes. Anyone got any ideas what we might want to do with it? So what I did look into was the JADES project, which was quite interesting. So we've got to have an acronym. Right?
Yes. Yep.
So JADES stands for JWST, already an acronym.
An acronym within an acronym. It's acronym inception.
All the way down.
Yep.
JWST, Advanced Deep Extragalactic Survey.
Nice, okay. And that means what exactly?
It's basically ramped up the Hubble Ultra Deep Field.
Oh, right, yes, which is, you will, listener, remember, we've shown this a few times now, I think, these amazing images from Hubble of just looking at space, what was, empty space, I'm doing air quotes here, and actually it's full of galaxies. This one tiny little block of sky has thousands of galaxies in it. The most amazing images. And this is doing that, but more.
Oh, yes. Very much more so.
Much more so.
So they're planning to spend already about 800 hours of JWST time.
Wow.
Just taking two fields of sky and just stopping and staring
just
at them.
Just looking at them. Really long.
So there are two fields. I was quite interested in this, actually. The two fields are called GOODS. They're from GOODS, the Great Observatories Origins Deep Survey.
Okay.
Great Observatories was sort of the 1990s project, 80s, 90s project of NASA, where they decided they would send basically a space telescope at every wavelength up.
Oh, that's right. Yeah. So you've got Hubble, but then you've also got Chandra, the
Spitzer
one, Spitzer. Yeah.
So they were called the Great Observatories. But then
and they're all in space.
Yeah.
Yep.
And then you had the ESA kind of came along slightly later and sort of did upgrades on those. So you had Herschel, XMM Newton was another one, X-ray telescope. So basically all the biggest and best telescopes across
all different wavelengths to be able to look at the universe in all different ways.
And they chose two patches of sky that they've been observing. One is in the north celestial sort of part of the sky around Ursa Major. And one is in the south celestial part of the sky, which is near Fornax. Mm-hmm. Now, the south bit actually contains the Hubble Ultra Deep Field itself as well.
So a bit we've already had a really good hard look at with Hubble. We're going to have a really hard look at with James Webb.
And we're going to go, and the great thing is we can see probably, maybe, hopefully, fingers crossed, these very, very first galaxies.
Wow. And when's that due to happen? Do we know? Let's turn the thing on first.
We've got to get it. I think we're at least a few months away still from our first science images, from what I understand. But, we're talking about probably months to years rather than decades, as it probably has been for many, many people's careers.
Well, Emily, you've given us something to be very excited about there. I know it's still, we still have to turn James Webb on properly yet. We have to take those first scientific images and do some real research and make sure that's actually working properly. But gee, there's going to be some really exciting stuff coming out of this thing.
Yeah, now I can understand when you read through that there's like I think there's about 4 science themes of JWST, and you read them and you think that's just all of astronomy. But it's nice to dig down and actually pull out the concrete things of, no, that's exactly why we're going to be answering that question about the very first stars, the very first galaxies in the universe. It's just because we're going to be able to actually see them.
Yeah, I kind of feel like at this point we should just turn this podcast into the JWST podcast. But no, we do talk about other things as well. It's just that it's really blooming exciting at the moment, and there's so much to look forward to. The other thing coming out of this episode is I never thought that I could have such deep feelings for a little galaxy forming and then potentially facing its doom. I'm a little bit sad about that. If people wanted to get in touch with the show to express their feelings about anthropomorphized cosmic structures, then Emily, how could people get in touch?
Well, I think you've probably got enough characters on Twitter just to get through at least the first part of those emotive responses.
Probably. Put some emojis in there to help us out. So how do they contact us on Twitter?
So you can at us, that's a thing, right? You
that's
can at us at SyzygyPod, SyzyGyPod.
Indeed. Also on the Instagrams on the same handle.
Yep.
And are we on Facebook?
Yeah, everyone's on.
Look, with all of these social medias, when we say we're on it, we do pop up from time to time. Yeah. We're trying our best. We are on Facebook. Just go and search for Syzygy Podcast, and you'll find us. We also have a website which has got all sorts of stuff on it, including a contact page and all of the past episodes. And a big shout out thanks to everyone who has supported the show, particularly through patreon.com/SyzygyPod, where you can go and financially support the show to help keep the electrons flowing through said website and everything that we do in this podcast. But the best way that you can support the show is by just telling everyone you know that we do a thing. If you know someone who would get a kick out of hearing about baby universes or indeed anything else in the cosmos, just tell them. Tell them that the show's on and they should go and listen to it, and it'll help us to rise up through the noise and be discovered by more people around the world. But otherwise, let's wrap it up there, Emily. So we're going to continue this baby theme.
Yeah, I think so.
What's coming up next?
It's a good question. We've gone in time, haven't we? We've gone from universes to the first stars and galaxies kind of maybe around the same time. So... it's a good question. Maybe we could go with kind of how stars are born today. Just a little bit different.
So not
to
the
those
first stars, but stars which are popping into existence around the galaxy and around the universe right now.
Right now.
Yeah, let's do that. Well, join us in a week or so's time, listeners, for that next one. Catch you in a week. See you later, Emily.
See you later.
Bye, everybody.
So it's a type of dwarf, which we've mentioned before. Oh, no, don't come in.
We have an intruder.
No, you still can't come in. It was a really big bumblebee.
Welcome to spring.